In this lesson, I will be talking about the polar form of a complex number. And before we explain what that is, we need to go back and look at the way we represent complex numbers at the moment. And we represent them in what's called Cartesian form or rectangular form. So the arcane diagrams we've been using all along, like this one here, what you do is you go across, for example, for the number z equals a plus ib, you go across a units and up b units, and that gives you the complex number z equals a plus ib. So this system where you go across and up to get to a number, that's called the Cartesian form of the number or the rectangular form of the number. Now, today we're going to look at an alternative way of getting to that number z, and that's called the polar form. So if we come down here to the end of the page, you'll see that we can also represent z in a different way. So if this is the number z here on the arcane diagram, we can, instead of going across and up each time, we can now go out a distance r from 0. In other words, we can find out which circle it's on, which of these concentric circles z is on, and also what angle it's at from 0. So the real axis is an angle of 0, so what's the angle it makes with the real axis? And that's it. So this is another system based on r and theta, where r is the distance or modulus. We came across this already in complex numbers. The distance from 0 is called the modulus. So r is the modulus, and the angle is called the argument of z. So the modulus of z is r, and the argument of z is theta. So that's what the rest of this page will be about. We're trying to get from the first diagram to that diagram at the bottom. How would you connect the two diagrams together? That's now the problem. So we'll go back to the first one, and we're going to put r, and we're going to put in r and theta in the first diagram and try and connect the two things together. So there's r. So that's the r, or the modulus of z, and there's the angle theta. So once more, we're trying to connect the old world of a and b, which is the Cartesian form, to the new world of r and theta, which is the polar form of the complex number. And we connect the two things together using trigonometry. We can now see that we're dealing with a right angle triangle here. And the first thing we can do is use Pythagoras Theorem. So that distance r, which is also called the modulus of z, which is written like this, is, if you look at the two distances here, a and b, well, a squared and b squared is r squared. A squared plus b squared is r squared. So r is then obviously the root of a squared plus b squared. That's a direct result of Pythagoras' theorem. So we've done all that before, and we've called it modulus previously. Now, the next thing is, so that's one half of the jigsaw fixed. We've connected the new world r to the old a and b system. Now can we do the same for theta? Can we connect theta to a and b as well? So we can do that by, theta is called the argument of z, by the way. So that's the name it's given, the argument of the number z. And you can see there that it's the tan of theta is b over a. The tan of theta is opposite over adjacent. So theta is the inverse tan, therefore, of b over a, if you want to write it that way. So again, tan is opposite over adjacent, which is b over a. So the tan of theta is b over a, or in other words, theta is the inverse tan of b over a, same thing. And now we can come down and use trigonometry to go a bit further. So over here, for example, we can say that the cos of theta is the adjacent over the hypotenuse. So the cos of theta from the diagram is the adjacent, which is the length a here, over the hypotenuse, which is r. So rearranging the formula now, a is equal to r cos theta. And we can do something similar for sine. So the sine of theta is equal to opposite over hypotenuse. So the sine of theta is equal to b over r. So b is equal to r sine theta, if you rearrange that formula. And now everything comes together, because if we now go back to our Cartesian form, which is z is equal to a plus ib, which we just had, this is what I started off with, we can now rewrite that as z is equal to, well, for a we can sub in, a is now r cos theta plus I times b, which is r sine theta. So that's the direct substitution. A becomes r cos theta. So A in the old world of Cartesian becomes r cos theta in the new world of polar, and B becomes r sine theta. So that's a direct swap, old for new. Now, we can take out the r, just factorize this, because now there's r in both terms. There's an r there, there's an r there. So we can just take out the r outside the bracket, and we get r into the cos of theta plus I sine theta. And finally we have it. So this is the big result that we wanted to get. We've now taken a number that was in Cartesian form, and we have converted it to polar form down here. The old form was in terms of a and b. The new form is in terms of r and theta. And the link, of course, is also there. We've shown the link above. The link is that r is the modulus of z, which is the root of a squared plus b squared. And theta, of course, is the argument of z, which is equal to the inverse 10 of b over a. And that's it. So we've basically gone from Cartesian to finally polar form. So this is polar form here. And that was the aim of, that was the first part of this lesson, is how you go from one to the other, from Cartesian to polar. And now we can express our number in polar form, and we can plot it on a diagram as shown below. And also we can see an application of this, of course, at this stage. It doesn't take long to figure out, I suppose. If you use this system, it could be useful for something like radar, where, for example, you're in an air traffic control tower here at the 0 point, and you're watching planes coming in. You're not really interested in how far across and up a plane is. You're more interested in how far out a plane is and what angle it's approaching at. And that would lend itself to polar form of expressing a number. Okay, so now the next thing we do now is some examples. So using this formula we've just derived, this polar form, we can now do some examples based on that formula. So here's the first example. So express z equals 3 plus 4i in polar form. Okay, so the first thing you do is you do a quick sketch, and you sketch where 3 plus 4i is. So there's 3, and there doesn't have to be accurate or anything like that. So there's 3 and 4, there's z. So z is there, and if we just do our modulus there and so on. And so you can see there that the distance is involved. That's 4, so that's 4i. So that's 4 units up. That's 3 units across. And that's theta, of course, and that's r. Now let's get r and theta. So the name of the game is this: draw the diagram, sketch the diagram, get r and theta, and then fill them into the formula, and that's it. So let's get r. Well, r is just the modulus, and we've already done that loads of times. So modulus of z is simply the square root of a squared plus b squared. And of course, this is a and this is b. So all you have to do here is the square root of 3 squared plus 4 squared, which is, if you work it out, the square root of 25, which is just 5. And the argument then, or theta, well, theta is just the inverse 10 of opposite over adjacent, which is 4 over 3. If you look at the right angle triangle we're dealing with here, the tan of theta in this right angle triangle, the tan is the opposite over the hypotenuse. Opposite is 4 over 3. So that's it. And if you work that out in your calculator, you get approximately 53 degrees. And now the last step is just fill in r and theta to our formula. So our formula is, of course, per polar form. We have it now from the last page. R into cos theta plus I sine theta, which is R is 5 into the cos of 53 degrees plus I sine 53 degrees. And that's your answer written in polar form. We have filled in R from here, and we have filled in theta from here. Now, one more example. So we'll do a slightly different one, where the diagram is more important. So express, we'll say it equals minus 2i in polar form. So again, you need a quick sketch to get started, to find out where it is first. So minus 2 and minus 2i is down here someplace. So we'll say it's about there. So there's r, there's your modulus. Now what's different here is, of course, theta. I emphasize at the start that theta is the angle from the real axis. The real axis is 0. So that means that theta is all the way around here this time. You've got to be careful with that. So that's theta. Which makes a slight difference when we're doing the angle, because if we now emphasize the right angle triangle again that we're working with, there it is. We're now going to have to work with our reference angle first before we get to full theta. So we call that r. Now, the opposite is 2 units. We don't care about basically the minus, because it's 2. When it comes to tan is the length of the opposite over the length of the adjacent. So it's 2 over 2. So we'll come back to that. First of all, though, there is no change with r. R is equal to the modulus of z, which is the square root of a squared plus b squared, which is the square root of, now again, be careful with your a's and b's. A and b there. A is minus 2 and b is minus 2. You don't include the I, so it's just the number part, the number of units up on the I, or up or down on the imaginary axis is b. Now, so it's minus 2 squared plus minus 2 squared, which is the root of 4, and 4 is 8, which is, if you work it out in the calculator, it's a bit simpler as 2 root 2. Now, we don't work with theta straight away. Now, that's the big difference here. We have to work with r first. So the tan of r, this reference angle, is opposite over hypotenuse, or opposite over adjacent, which is 2 over 2, which is 1. So r is 45 degrees. From the tables, if the tan is 1, r is 45. You can get that in your tables or in your calculator. Or if you want to work in radians, it's pi over 4 radians. Same thing. Now, however, that means that theta, to get theta, we have to go all around now. So we have to go around here to 180. This is 180 right here. And we've got to add on r to 180. So to get the true value of theta, you've got to add 180 degrees. So it's 180 plus 45. Or if you're in radians, it's, well, 180 is pi radians plus pi over 4. Now 180 plus 45 is 225. Now pi is like 4 pi over 4, so 4 pi over 4, and pi over 4 is 5 pi over 4 rads. And that's it. We now have, again, we have the two things we need to write in polar form, r and theta. So let's fill in those into our formula, and we have the answer then. So z is now equal to r times cos theta plus I sine theta. So z is equal to r, which is 2 root 2, the modulus or radius, by the cos of 225 plus I sine 225 degrees. Or if you want to work in radians, depending on what the exam question wants, you could say 2 root 2 cos 5 pi over 4 plus I sine 5 pi over 4. And there it is in polar form, in degrees or in radians, whichever you prefer. That's the end of the lesson on polar form.